Hey guys, so if you are struggling with acids and bases, this is going to be your guide today. We're going to help you out with all this stuff. So in the other video, I talked about acid-base reactions and redox reactions in a different video. That's where I talked about Bronson-Lowry definition and conjugate acids and bases, what an acid-base reaction is, like what it looks like, the anatomy of it. I'm not talking about that today. Today, I'm just going to mainly focus on these 2 points. Acid-base strength, so pH, Ka, pKa, what those terms mean and when we're comparing them. Also calculating them, how we can calculate the pH from an acid-base like situation. And then going between those calculations, if we have pH, pOH, H3O+, kind of moving through those calculations and cycling through that. And then buffers. We're going to talk a little bit about titrations and not titrations actually. Well, yeah, just buffers and like what a buffer is and calculations with those as well. Okay. So I guess just one reminder with conjugate acids and bases that's important. Typically, if you're identifying a conjugate acid and a base, the acid is typically the one that has a hydrogen. This isn't always the case, but typically if it's like which one's the acid and which one's the base, usually you're going to see the acid have a hydrogen because that's the proton. It's a proton donor, so that's when it's going to donate. And a base is going to have no hydrogen. It's going to be the same thing with no hydrogen and a negative charge. That's really common to see when you're comparing acids and bases. Really don't overthink it. Usually the acids are just going to be the same, but it has an hydrogen. It might not even be like have a charge, like for example, hydrogen sulfate, this H2SO4. This is the acid, and this would be the conjugate base, HSO4. One of these. And see, this still has a hydrogen, but it has one less hydrogen than this one. So this would be the acid, this would be its conjugate base. So just identifying those and understanding the difference between conjugate and then its conjugate acid, conjugate base, whatever that is. Okay? Anyways, let's talk about Ka. What does Ka mean? And if you watch my video about equilibrium, this is going to be really helpful for that. If you haven't watched it, I would really recommend understanding equilibrium more because that's what this is. If you remember in equilibrium, what we had is we had a K. This was our equilibrium constant, and then it had to do with our whatever the reaction was. So it's like you'd have your equilibrium expression, you'd have like a value in brackets, and then this, okay? The brackets, if it's in brackets, it means concentration. Okay, so if I'm like brackets of this, if I put it in brackets, the value that goes inside is the concentration of NO3 that I have, right? Which isn't like, so if I had 0.1 molars concentration of NO3, I'd put that concentration in here. Okay, so that's what the brackets mean. That's why we use specifically brackets, okay? But if you remember this equilibrium expression, this is what this is. And with acids and bases, this is just an equilibrium expression that we're using with acids, okay? And this is, it's Ka because it's a specific kind of equilibrium constant. This is called the acid dissociation constant. Dissociation constant. Okay? And basically this is telling us like, this tells us how much of the acid is dissociated because it's like products favored. That's usually a higher Ka value, right? That means products are favored. So a higher Ka value, again, is also going to mean it's like a stronger base, right? Wait, that's right. Yeah. So a higher Ka value means a stronger acid. Let me grab the formula so it looks like this. In the actual just like formula here, we have A minus, H plus, and HA. And the reaction that we're basically looking at here is this. We have HA, which is our weak acid. H is the proton, right? And this is just the acid, right? And then it dissociates into H plus ions and A minus. So this is the conjugate base. And these are the H plus ions, these are what make a solution acidic, which I'll show you that in a second. Okay, but this is like the reaction. It's just when an acid dissociates. Okay, so you take any acid, HCl, it's going to split into H plus ions and the conjugate base. Okay, so this is just like a general thing. And then its expression would look like this. We have Cl minus concentration, the H plus concentration, and then the reactants down here, the HCl concentration. Okay, so if you remember equilibrium expressions, this is exactly what this is. It's just the equilibrium expression for an acid dissociation. Okay, if there's more products than reactants, if this dissociates a lot more and there's like, let's say there's like 90% products, that means there's a ton of H plus ions. It's going to make the solution very, very acidic. And that means our K value is going to be super, super, super high because products are favored in this case, right? If it is a low K value, right, that means there's going to be more reactants. If reactants are favored, let's say there's 90% of these and 10% of these, right, that's going to be a really weak acid because there's not very many H plus ions, right? There's not as many H plus ions, so it's not going to make the solution as acidic, so therefore it's just going to be a weaker acid. Okay? That's kind of what this is showing. Yeah. I just lost the train of thought. Yeah. Here, let me write this better in notes so you can kind of see what it is. Okay, so here's our just general expression here with the general reaction. Okay? Let me get you some real life Ka values. So, first off, here's one, HNO2. Okay, it's going to dissociate into H plus and NO2 minus. Okay, this is an acid. Spoiler alert, it's a pretty strong acid. Actually, let me get you a stronger one. Just so you can kind of see the difference. Here we go, that's good. We're gonna just do HCl, the one I was doing before, okay? So HCl and then H plus and Cl minus, okay? So this is hydrochloric acid. Its Ka value in its expression, so you don't have to like write out this expression. I'm just trying to help you see like what this is so you can kind of connect some dots here and it'll make it easier for you for what Ka is and everything. Okay, so, and if you're doing Chem 105 and Chem 106, this is going to be super helpful for you because you will be doing a ton of this. So its Ka value, okay, is 3.16 times 10 to the 9. Okay, that's a super, super high Ka value. And this is a very, very strong acid, HCl. So this is strong acid because remember the trend, higher Ka equals stronger acid. Okay, so that means when HCl dissociates, it's gonna mostly like create 99.999% of products and then like 0.0001 of reactants. So most of it's gonna be products with the H plus ions are going to mix with the water and make it really acidic. Okay? So that's what's going to happen here, and that's what this is saying, because high K value equals product favored. Okay, just like we talked about. So we're just relating it to acidity now. Okay, here's another example for you. We're going to do, here's our next acid. We have HCOOH. HCOOH. Okay. Actually, yeah, that's good. It dissociates into H plus ions and HCOO minus. Okay, so here's the conjugate base and here's the ions. This one is a weaker acid because its Ka value, we put the reactants on top. We put those there and put this on the bottom of our expression. The Ka value for this is 1.8 times 10 to the negative 5. Okay, so this is its Ka value. So you can see the difference here. This is 3.6 times 10 to the 9. This is 1.8 times 10 to the negative 5. So this is like a decimal. And it's like, I'm pretty sure the rule is if it's greater than 1, it's considered a strong acid. If it's less than 1, it's considered a weak acid. which makes sense. That's kind of our same rules with what was I saying? With equilibrium, right? If Ka is greater than 1, it's strong. If Ka is less than 1, it's weak, right? This isn't a trend you really need to know. I would just know the difference between like which one is stronger. Like if I gave you a list of Kas and said, which one of these is the strongest acid in this group? Know how to differentiate that. And it's just going to be the biggest number, whichever Ka is the biggest. Okay. Now here's the flip. This is where it might get tricky and you need to really pay attention. So there's Ka, but then there's also pKa. Okay, and if you've taken calculus, you probably understand logs and like logarithms, and I haven't taken calculus obviously because I didn't even think of what it is, but that's what this is. We're doing an anti-log. That's what it is. So P in mathematical like language means anti-log. So there's log and then there's like anti-log, which I think is like negative log. I'll show you how to calculate it, so don't worry. Basically, what we do here, this is kind of like pH, right? We have pH, which I'll talk about after this. This is it's a soup. You know what pH is? It's a range of 0 to 14 that tell us the strength if it's an acid or a base. And what pKa does is it helps us really numerically just compare different acids so that we can tell which ones are stronger and weak. Instead of having these huge massive numbers and these really tiny numbers, we're just condensing them into smaller numbers to make it easier to compare. Okay, so the pKa for HCl, what we would do is find the negative log of HCl. So we're going to do first what I do. You may have your own way of calculating it, but first you do just 1 divided by the number, 3.116 times 10 to the 9th. Okay, and then, so I'll do this on my calculator over here. So 1 divided by 3.16 9. Oh, sorry, 9. Okay, that gives me that. And then we're just going to do, it gives me an answer, blank, and then log of blank, and then we just do the normal log, not this one. Do the normal log. Since we did the 1 divided by that does the anti-log, and now we're going to do the normal log of this, and that gives us our answer, negative 9.5. Okay, so the pKa is negative 9.5. Okay, so again, just a review, I guess I'll review that in a second. That's how you do it. 1 divided by that and then log of the number. Okay, so that is where we get pKa values. And as you can tell, it's just a negative 9.5 number. Okay, let's do the other one. Let's do HCl minus. So let's find the pKa of this. We're going to do 1 divided by this number. So 1 divided by 1.8 E negative 5. That's just short for scientific notation if you didn't know that. Okay, there's that. And then we're going to do the log of that number. And we get 4.74 is our pKa of this. So here's our two pKa's. What do you see? Now the roles are flipped. A lower pKa is a stronger acid. Okay, so the strongest acids are going to have a negative pKa, like negative 9.5. A weaker acid is going to have a positive pKa, like 4.74. Okay, so lower pKa equals stronger acid. Okay, so it's the opposite here. Make sense? Know the distinguishing between those and understanding acid strength. And this is for stronger acid. Base strength is a little bit different because what you would do with bases, it's like the same thing, but instead of Ka, you would get a Kb value. I think you did learn about this. It's just the same expression, but it's on the base end of it where we take the OH minus concentration and then I don't even think you need to know that. So, but it's the same concept of this. For Kb, higher Kb equals stronger base. Okay. And then the same trend with pKa. If it's pKb, it's a lower, it's stronger. Okay, but it's going to be the opposite. So higher Ka, if it's a lower Ka, right, it's going to be a weaker at base. Oh wait, sorry. Lower Ka is going to be stronger base. Okay, so just, I hope you're seeing these trends and it's not like, whoa, this is all confusing. Just remember Ka, if it's a big number, since the acid dissociation constant, it means it's product favored and stronger acid. Okay, and then pKa is just the opposite. Lower number like this is a really strong acid. And then if you're thinking about a base, like if it's a really low Ka, it's going to be a stronger base. But anyways, hopefully this is making sense. Please just ask me questions. If it doesn't, like, just send me a message. Okay, but that's the gist with Ka. Okay. Yeah, so if you want to compare acids, figure out which one's the strongest or not, you can convert it to pKa, or you can keep it at Ka and just look at the trends and see which one would be the strongest, right? Okay. Just making sure I didn't miss anything here. Okay, cool. So now here's another, we're going to get into just pH now. It's a really similar concept. Maybe you should have done this first before Ka, but hopefully things will click for you. So we're going to use another K value because we're using this equilibrium stuff a lot. And this is just a general concept. Basically, in pure water, when you have water, right, you have H2O molecules. What they do naturally is they ionize with each other. So they have this acid-base relationship. In my one video, I talked about how water can be an acid or a base. And they kind of do have this relationship with each other where a water could steal one of the protons from another water, right? So like, let's say this water over here stole a proton from this water, okay? Then this is going to go H3O plus, and this water just lost one, so it's going to go OH minus. Okay, so that happens just all the time in regular water. It's just like a normal thing. So we'd have like a bunch of OH minuses and then some H3O plus, right? Just kind of bouncing each other out like that, whatever. This is called the auto-ionization of water, okay? And you don't really need to understand this itself, but I just want, this kind of helps understand what pH is and how to work between it, okay? So I'm going a little more in depth than you probably need to, but for those students who need this in the future, this should be helpful. So the expression for this is, we just have H3O plus and OH minus equal this equilibrium constant. And there's a fixed number for this. We actually know what this is. It's always 1 times 10 to the negative 14. Okay, so this is our Kw value, which is just the dissociation constant of water, Kw. Okay, and it's this number. So really lock down this number. This number is really helpful, and you kind of have to memorize it. It's not very hard to memorize, but this is where we get the concept of pH. Okay, so I'm going to try to explain this the best I can. If basically, yeah, so water reacts to form ions. So what we're doing with pH in water, what the heck? I'm so sorry. Oh, we're good. Here, I'm gonna do this really quick. I'm gonna close this. Sorry. I do this just because it helps my thing work better sometimes. Okay, so in water, let me draw my nice cup of water here. Let's say normal water, neutral water has an equal percentage of both ions. If water has a greater percentage of H3O plus ions than it has OH, right? If this is 50-50, both 50%, then it's going to be neutral. It's going to be a neutral pH. If there's more H3O plus, that means I have more H plus ions, which is going to make the solution acidic. Okay, so this is the one that causes it to be acidic, is our H3O plus, and our OH minus is the one that causes it to be basic. Okay, If there's more OH minus concentration, if there's 75% of this and 25% of this, it's going to be basic. I can draw this better. Okay, so 25%, 75% equals acidic. And there's numerical ways to see this, but I'm just hoping you understand the concept. If I have 75% OH concentration, 25% H plus concentration, or H3O plus, it's going to be basic. Okay? And this is just if we're looking in water, we have our H2O, this is all H2O. If we have more of this, H plus, H plus, H plus, H plus, H plus, right? And then there's one OH minus. This is going to be a really acidic solution. And this doesn't happen naturally. This happens when you put other things into water. Typically, at its most natural form, water is at 50-50, okay? It has 50% H3O plus and 50% OH minus, because it's just like normal water. It's just H2O at its natural form. It's not really ionizing, it's just normal. So we have an equal concentration, and our pH is going to be 7. That's like neutral pH, right? So if I were to add, remember back here, if I were to add this, HCl, okay, I add HCl to water. And remember when I talked about how it dissociates, so HCl is going to be added to water, it's going to dissociate into H plus and Cl minus, okay? So we're adding just a bunch of H plus to water, H plus, H plus, H plus. And what does that do? It ups the concentration of our H3O, of our H plus in here, right? And what would typically happen is we would have it would up the concentration of H plus and then lower the concentration of OH minus, okay? So what's going to happen is it's going to become more acidic, okay? That's just how it introduced into solution, and that's simply the way that water would get more acidic is if you add something else, okay? I'm not going to go too deep into that. Okay, yeah, so normally I'm going all around the bush here. The concentrations of this, if this is 1 times 10 to the negative 14, then these values at base value are going to be 1 times 10 to the negative 7, right? And 1 times 10 to the negative 7, because that's what it equals. If we know what this answer is always, then that's what these two are going to equal, okay? So the way that we find pH, how we calculate it, let me just show you how to do this. We're going to take our H plus concentration, so take that, and then we're going to do P of H, pH. See that? We're going to do the negative log of our H plus concentration, which in this case is 1 times 10 to the negative 7. And then that is going to give us our pH value. So let's solve for that. Let's do, again, 1 divided by 1e, negative 7. What is happening? Sorry. 1e negative 7. There we go. Okay, and then we're going to do the log of that, and we get 7. Okay, so there's our pH. pH of neutral water when it's at this concentration, our pH is 7. Okay? If we were to add HCl to water, it's going to increase our H plus concentration. So let's say it increased the concentration to 3 times 10 to the negative 3, right? This is an increase because before it was at 1 times 10 to the negative 7, so there were 0.0000007, and now, 0.001, but now our concentration is 0.003. 1, 2, 3, yeah. So we increased the concentration. We added more H plus ions because we chucked HCl in there. So let's calculate what this pH would be, okay? We add HCl to the water, and we're going to do the negative log of that. So 1 divided by 1 divided by our number, okay? And then do the log of that, 2.5, okay? So our new pH is 2.5. See See that? It's way more acidic because if you remember the range here, 7 is neutral. Anything 0 to 7 is acidic. And anything 7 to 14 is basic. Okay, and where does HCl fall? This isn't the actual pH, but you don't need to know the actual. I'm just showing you how to calculate this. It was 2.5, so that's going to be like right here. So that's very acidic. And this is strength. The farther over here it is, the stronger it is. Okay, so we have a very, very acidic, very, very acidic solution. Yeah, lots of H plus ions. Okay, hopefully that makes sense. If we let's say we put in a base, NaOH. This is a really strong base. Okay, so we should get a pretty high pH when we do this. Let's see. Let me look up the value here. Okay, so if we put NaOH into water, we put it into our water, and it makes our concentration, this is what it does to our concentration. We're looking up here. Okay, it goes to 1 times 10 to the negative 13, and then we would have 1 times 10 to the negative, it would just be 0.1. Like that. Okay, so this would be our OH minus concentration, and this would be our H plus concentration. Okay, so this is if we added a base to water, and it obviously there's a really, really small concentration of H plus ions, and there's a huge concentration of OH ions. Okay, if we use this number though, we'd be solving for the POH, right? But we want to know the pH. We can't solve for the POH. All you would do is take this value, do the negative log of 0.1, and you would get the POH value. It'd be a really low number. But usually we typically use pH. Let's find the pH of NaOH, okay? Again, same thing. Here's our 1 times 10 to the negative 13. So we do 1 divided by 1 times, I think I'd be good at this now after taking so much chemistry. Okay, log of that. 13. pH equals 13 of NaOH. So this is really, really basic, okay? I hope this makes sense. All this conceptual stuff, if you just want to memorize the math to it, that'd probably get you through everything and you'd be fine. For me, it just really helps to know the conceptual stuff. And it's also really interesting. You've probably wondered about pH your entire life. Like, what is that? When it says like pH in certain things, like what's the pH of urine, or you need a healthy pH in your mouth with your toothpaste, stuff like that, you know? That's what this is. Certain places thrive in better pHs, right? They survive better in a more acidic pH. For example, your stomach is very, very acidic. There's a very low pH in your stomach, okay? Because there's a lot of acids, there's a lot of H plus ions in your stomach, and that helps dissolve down food and break it down. But when you throw up, it burns and it hurts a lot because that's what acids do to your body. So there you go. That's what acids and bases are. I know you know what these are. A lot of solutions like bleach and cleaning solutions are bases, right? So these are part of your everyday life. So you're learning about them now. Okay, so here's the gist of what I want to get to. So what's important for you to be able to do? Sorry, one sec. Okay, here is the base of what I want you to be able to do. If I give you this number, I say, if my OH, here's my OH concentration. If this is 4.2 times 10 to the negative 5, okay, what is my H3O plus concentration? What's my H plus concentration? What does this mean? Well, it's just super, super simple math. what I was given was this value. What I want to find is this value. So all I have to do is plug this in. 4.2 times 10 to the negative 5. Okay, I'm not using brackets just because we're just looking at as algebra right now. Okay, equals h plus. That's what we're solving for. So what do you do to solve this? Well, you just divide this on both sides, and then you would get your H plus concentration. Okay, so let's do that quick. E negative 14 divided by 4.2, E negative 5. And what does that get me? My H plus concentration is 2.38 times 10 to the negative 10. Cool. So I found my H plus. I have my H plus and my OH. Now, what's the pH? Okay, how do I do that? Well, all you do is the negative log of my H plus concentration, which is 2.38 times 10 to the negative 10, right? 1 divided by that number, and then do the log of that, and the pH is 9.62. There's my pH. Is it basic or is it acidic? It is basic, right? Because it's above 7. That's what you're doing. That's the calculations. And you really want to be able to bounce between all of these, okay? Let me do a different one. Sorry, I know I went through that really fast. I'll give you a second to like breathe after this, okay? Okay, so let's see what we're doing. If H3O plus is 2.9, okay. Let me do this. I'm gonna give you, here's our pH. pH, actually I'll let you practice on what I just showed you. Okay, so H3O plus my H plus concentration is 2.9 times 10 to the negative 3. What is OH minus? What's my concentration for that? And what is my pH? Okay. Solve this. Should be pretty simple to do. I'm going to do it in my calculator over here, and we'll see if we get the same answers. Okay. Okay, I guess you can pause the video. I'll explain while I'm doing it. It's kind of weird, just do it quietly. So 1 times 10 to the 14, we're going to divide it by our H plus concentration. It's going to give us our OH minus. So our OH minus is 3.4 times 10 to the negative 12. Okay. I don't need this value to calculate my pH. So I'm just going to use the same number. 1 divided by 2.9. 2.9. to the negative 3. And the log of that, 2.5. So this is a really acidic solution. Okay? Makes sense? And that makes it does make sense because if we look at our two concentrations, we have a lot more H3O plus than we do have OH. We have a lot more, so it's going to make it a more acidic solution. Okay? Let's try another one. This time, I'm just going to give you our pH. This is where things get a little trippy. So my pH is 10.2. Okay? If that's my pH, what is my OH minus concentration? Okay? This is a really basic solution. It's pretty basic. So I want to know how many OH ions I have in the solution. So what could I do? Okay? For this, we already have a pH, right? The negative log of our H plus is 10.2. So what we would do here is we need to solve for our H plus concentration, and then we can solve for our OH minus concentration for our H plus, okay? So we need to do the reverse of this. We need to do, which is pretty simple. All we would do, take our pH. There's this little, if you look with log, this button right here, I'm highlighting it white so you can see it. Second, and then this, it's the 10, and then there's a little exponent on top. We're going to do to 10.2, okay? This is going to give us that, but since it's negative log, we need to divide it by that again, and it's going to give us our H plus concentration, okay? So if you forgot what that is, it's this button, second, 10, it's like a 10 to the X, so plug your pH in there, and then do 1 divided by that, and then that gives you your H plus concentration. Okay, cool. Hopefully that makes sense. If it doesn't, please, this is super simple. So if you're not getting this from this video, then I hope you'll reach out to me and figure it out. Okay, so H plus concentration is 6.3 times 10 to the negative 11. Okay, this is not what I've been asked for though. I'm asking for my OH concentration. So I would just divide 1 times 10 to the negative 4 by my H2O plus concentration and solve for that. Okay, so 1 E negative 14 divided by 6.3 E negative 11. Okay, and it gives me this 0.0 OH minus is 1.6 times 10 to the negative 4. Okay, there is my OH minus concentration, or my hydroxide concentration, if you remember your polyatomic ions. Sweet. So hopefully this seems pretty simple. Hopefully this makes sense transitioning between the two. You want to be able to solve for H plus. You want to be able to solve for OH minus. You want to be able to solve for pH. And then the only other one I didn't really do is pOH. If you're given that, like if I was given a pOH value, all it is you would do the reverse log like I just showed you down here, right? Do the 10 and then the exponent of that, and then 1 divided by the answer. And that would give you your OH minus concentration instead of your H plus, okay? So these are all just super related to each other, and you can bounce back and forth between all of them, okay? So hopefully that makes sense to you. The last thing I'm going to cover is buffers. Let's do this. I feel like I'm missing something, but it's just because I don't have anyone on the other end that can ask me questions, because that's what I need. But again, please do. So buffers, let's do this really fast because I don't want to take up more of your time. I like this stuff, so I can explain on and on and on and on and on. But so what a buffer is it's a solution that resists changes in pH. Okay. Solution, sorry, whoa, that resists changes in pH when acids or bases are added. Cool? So typically, like I said, if you have a solution of water and you just add an acid to it, it's going to make it acidic like super fast, like immediately acidic, right? What a buffer is, it's a solution that resists that, and it doesn't let the pH change very much. So if I add acid to this buffer, it's not going to change, and you probably learned about it and what it is. I'm just going to explain more simply today of what it really is. An example is your blood. In your bloodstream, blood is a really good buffer. What it does is it keeps your everything at a pH of 7.4. Is it keeps all your blood stays around this because it needs to be at this neutral pH. It needs to be like this. So if you drink like orange juice with a lot of citric acid in it, or something like that, or if you're running and you build up a lot of lactic acid, it's going to throw a lot of acid into your bloodstream, but your blood resists it and it stays at 7.4. If it wasn't a buffer, your blood would start to get super, super acidic, and it would go to like a 6 and then a 5, and then you would die. So that's why we have blood as a buffer. Okay. So that we can drink orange juice. This doesn't mean that a buffer is always keeping it neutral. Doesn't always, like you can have a buffer at 2.5 pH, but what the buffer does is it makes it so you can't change. It puts like a wall around it and it says, no, you're an acid, you're a base, you can't affect my pH, I'm going to stay where I am. I mean, it might fluctuate like 2.6, 2.7, but nothing more than that that's going to really make a difference. Okay, so that's what a buffer is. It resists that. Yeah, that's really what it is. It's also helpful for experiments if we want to test acids and bases and do experiments with them, but we don't want to actually like make the solution more acidic. We just want to test, but things like that. The equation you're going to use for this is called the Henderson-Hasselbalch equation. Okay, I'm pretty sure you have it on your exam, so don't worry about that. But here's what it is. This is what we use to build buffers. Is pH equals the pKa plus log of sorry, one sec. Yeah. Log of the base over acid. This is our equation. Okay. Let me just give you a practice problem to show you what this could look like. I got this just from your lessons, from lesson 5 acid and base 1. From the buffer section, I got it from this. So this, you probably have already done this, but if not, here you go. If you have, here's a good review. Okay. If our ratio, A minus, this is a ratio of our conjugate base to the acid. If this ratio is 0.9, okay, what is the pH of lactic acid solution? Okay, here's your problem. So our ratio is 0.9. So that just goes right here into this part. This is the pKa of whatever the acid is. So in this case, it'd be the pKa of lactic acid. The number is 3.85. Okay, and it's saying what's the pH? Okay, so this is basically saying, this is. I won't explain it too complex. You hopefully, if you learned about it, then great. But if not, I'm just gonna show you how to do the math today. Okay. So we just plug this in. Literally, log of 3.85. This isn't reverse negative log. It's just normal log, and then our pKa, which is 3.85, and that is gonna equal our pH. Okay. So we solve for it. So 3.85. Let's do this first. Let's do the log of 3.85. Wait, I did that wrong. The log of 0.9. That's our ratio. Sorry. Log of 0.9. And then we're going to add that to 3.85. And our pH is going to be 3.80. Okay? And this equation just helps us, like, there's a point in a buffer when the pKa is very, very similar to the pH of the acid. So this helps us determine the pH based on the pKa. So it makes us really easily help us know the pH of our solution, our buffer solution, just by the acid that we're adding. So that's kind of what it is. You don't really need to know that. But that's how we would use this equation. Okay, let's say it's given to you another direction. If it said, if pH of lactic acid solution was 4.25, what is the ratio of conjugate base to acid? That's what this ratio is. We have in our equation the A minus, remember that's our conjugate base when it's dissociated, and HA, this is just representing our acid. So our acid dissociates and this is conjugate base. It's the ratio of how much base we have to the acid, okay? And the less base we have, the more acidic it's going to be because we have less base but more acid. So we just plug this into our equation. We have 4.25 as our pH equals the pKa, which is the same as before, 3.85. I'm going to say, put that on just, okay? And then we add it to the log. And this is just 3.85 because it's lactic acid. It's not always this. It depends on whatever the acid is or the base that's in this solution. Log of the ratio. This is what we're solving for, is this whole ratio. It's not saying solve for the conjugate base concentration or the acid concentration. If it did, you'd have to do some more calculations. But if it's just asking for the ratio, just solve for this. So I'm just going to put X because it's just looking for what's in that parentheses. Okay. So first, just order of operations. We're going to subtract 3.85, so 4.25 minus 3.85, 0.4, and then log of x, just like we did before. Remember this, to reverse like a log or undo it, we're going to do the 10 exponent, and then 0.4, and then that's going to equal, our ratio equals 2.5. Okay, so that was our ratio. Easy enough. That's Henderson-Hasselbalch equation. Okay, I'm not going to go into more in depth just because of time, but you guys didn't even learn it that in depth. I don't remember, but that's really what I would focus on for acids and bases for this unit. Hopefully that all made sense. If you have any questions, please reach out to me, and I will be here to help you guys.